right, hello students. So we're looking here at problem 16. Lovely little problem using De Moivre's theorem to show that z to the n plus 1 over z to the n equals 2 cosine n theta, where z is a complex number of the form cosine theta plus I sine theta. Great. So I'm going to write, if z is cosine theta plus I sine theta, I can write it as e I theta, e to the I theta. And then using my exponent laws, I can write that as e to the I n theta, z to the n, because you multiply a power to a power. And then 1 over z to the n is the same as z to the negative n. And so that's going to be e to the I negative I n theta. And so then all of that together, z to the n plus 1 over z to the n is equal to e to the I n theta plus e to the negative I n theta. And that might not look like anything too exciting yet, but what you can do then is write it in terms of the cosine theta plus I sine theta. So the first part here becomes cosine of n theta plus I sine of n theta. And the second part becomes cosine of negative n theta plus I sine of negative n theta. And the nice thing about cosine is that the cosine of a theta value is the same as the cosine of a negative theta value. Just do it with your fingers on the unit circle. If you rotate in opposite directions, your fingers will always share the same x value. So I know that this first cosine of n theta is identical to the cosine of negative n theta. And so I can combine those like terms to get 2 cosine of n theta. And if you do that with your fingers, you'll notice that one finger moves up and the other finger moves down. So they have the same y value but opposite. And so when I try to mark that, the sine of n theta and the sine of negative n theta are opposites. And they cancel out, and we have the result that we wanted, 2 cosine n theta. You should maybe have these memorized at this point, just that cosine of negative x is equal to cosine of x. It's an even function, if you remember that term from several months ago. And that sine of negative x is equal to negative sine of x. So you can either get it by thinking of the graphs and how cosine is symmetric across the y-axis, or you can get it by thinking about the unit circle and how the cosine values are the same regardless of your direction of rotation, and sine is antisymmetric. Okay, there we go. So we have 2 cosine of n theta. We don't need this anymore because it was a show that sort of problem. So we already know the answer. Part B, consider the binomial expansion of z plus 1 over z to the fourth. I'm going to just draw Pascal's little triangle. Just to get the fourth row, because that tells me the coefficients of the expansion. And so when I look at z plus 1 over z to the fourth, I'm going to rewrite it in terms of z to the negative 1, and I'm going to just read off the coefficients from the fourth row of Pascal's triangle. So we have 1 z to the fourth plus 4 z to the third times z to the negative 1 plus 6z squared z to the negative 2 plus 4z times z to the negative 3 plus 1z to the negative 4. That should be okay. Simplifying a little bit, z to the fourth plus 4z squared plus 6 plus 4z to the negative 2 plus z to the negative 4. Now this is super nice here. We had a result that z to the n plus 1 over z to the n equals 2 cosine n theta. And here I see a z to the n plus a z to the negative n. Here I see a 4z to the n plus 4z to the negative n. So I'm going to use this formula twice, and just notice that the n as a power matches the n as the multiple. So I have 2 cosine of 4 theta, and I have 8 cosine of 2 theta. because of the 4 multiplying in front of it, and then plus 6. Okay. Now, what was I supposed to show? I was supposed to show that cosine to the 4th theta is equal to that. And I have a lot of it, but I don't have the 16th in there, and I don't have the cosine to the 4th power. So let's look at how we can figure out cosine to the 4th power from this here. What am I missing? Where does the cosine to the 4th power come from? So the original problem here, z plus z to the negative 1, we're going to use that again. We can rewrite this as 2 cosine of 1 theta, or just regular theta to the 4th power. So if I slide that part down here, 2 to the 4th becomes 16, cosine to the 4th theta there, and we can divide by 16 to get the requested result. There we go. I got scared for a second, but wishful thinking, right? It's always going to work out as long as you just follow your steps of algebra. So now we have another identity. Great. Clearing the screen and moving down a little bit. Oops. Let's see. Come on, slide down. So now we're supposed to do an integral. Great. Cosine to the 4th theta would be kind of hard to deal with as just a regular integration problem, because you might need to use some trig substitution, you might need to use some trig identities, but we actually have just worked out in part C this wonderful trig identity here. And so I'm going to take the integral and just rewrite it in terms of the identity we just proved. So the requested integral is the same as 1/16 times the integral from 0 to pi over 6 of, and I pulled the 1/16 out, so we have 2 cosine 4 theta plus 8 cosine 2 theta plus 6 d theta. Integrate everything. It's like a mini u substitution here. So the integral of cosine is sine, and because there's a 4 theta, we're going to divide by 4. So we have 2 over 4 sine of 4 theta plus 8 over 2 sine of 2 theta plus 6 theta, and that's evaluated from 0 to pi over 6. Okay, let's see. The nice thing about sine of 0 is it's equal to 0, and so all we really need to do is think about the pi over 6's. So I have 1/16 times 1/2 times the sine of 4 pi over 6, so 2 pi over 3, plus 4 times the sine of 2 pi over 6, which is pi over 3, plus 6 times theta, so 6 times pi over 6 is pi. Let's see, the sine of 2 pi over 3 is square root of 3 over 2, so we have 1/16 times 1/2 times square root of 3 over 2, plus 4 times sine of pi over 3, which is also square root of 3 over 2, plus pi. So that gives me 1/16 times square root of 3 over 4 plus 2 root 3 plus pi. I mean, that's actually fine as an answer. I guess I could do a little bit better, making this into 8 root 3 over 4. So I guess I have 1/16 times 9 root 3 over 4 plus pi. Maybe you want to distribute that, 9 root 3 over 64 plus pi over 16. Really, for purposes of my test, I'm okay with this answer, I'm okay with this answer, I'm okay with that answer. It's all the same to me. The relevant thing really is that you're able to use the prior result to express cosine to the 4th in terms of the first powers of cosines, and then you're using that mini u substitution to integrate and divide by the linear coefficient of theta. All right, ask questions or let me know where I screwed up.